Okay, thank you. Yeah, so that's the final lecture. I'll give some final non-vanishing statements and some other applications of this invariance. So let's start with some recollection of what we have achieved so far. So recollection. So we work with algebraic varieties over a field, and we are playing with this invariant, which I call C, from Urech into certain other abelian groups. So this is n is the dimension of x, and we are going from birational maps of x into this thing spanned by birational types of divisors. And I want to write again this non-vanishing table from the first lecture and to demonstrate what we have studied so far. So the table, okay, I don't put dimension 1, it's trivial. So start with dimension 2, dimension 3, and higher dimension. So, and depending on the field, we have slightly different results here. So for surfaces, the basic result is that the invariant is 0 for perfect field K. So I wasn't, okay, so I used this perfect a lot, so just to be specific, so characteristic 0 is okay. So perfect means every finite extension is separable. So we can use Galois theory and minimal model program with Sarkisov-Link factorization. So for example, finite field is okay. Even though it's characteristic P, it's a perfect field. However, if you add a variable to finite field, it's not perfect anymore. You can take P roots of this, and it's not known. So there are some subtleties which go into this proof. This is surfaces case. The next, and okay, this is kind of important because when we do this fibrations over the base, even if we start with a perfect field, fields like this stop being perfect. So it's kind of useful to have statements like this, but we don't quite have it here. N equals 3, so there are two different cases. We did prove that we have full vanishing for complex numbers, or more generally, algebraically closed field of characteristic 0. There were these two cases, rationally connected and non-rationally connected, but this is fully established now. And also, I gave an example, like I explained how this is the case for some what I call small fields, so number fields or function fields. There was some example with funny genus 1 curves with no points, how they were not matching up on the two sides. And of course, if we pass to algebraic closure, all these kind of examples have to disappear. So therefore, it's quite subtle, twisted forms, which are not isomorphic. Yeah, and what we haven't talked much is this column. So what I want to claim is that this is like basically always non-zero. So I want to say for, right, and non-vanishing, we can specify when it's non-vanishing. So it was for P3 and higher dimensional Pn by keep multiplying with P1. Okay, so here we have non-vanishing for all K of characteristic 0. One can weaken it somehow, but maybe in dimension 4, that's what we have. And again, we can take Pn. Yeah, and one of the main things today, I'll be explaining how this goes. Yeah, and just to emphasize, the standard application is that when the invariant is not 0, the corresponding birational group not generated by elements of various types, such as most generally we can say pseudo-regularizable maps, conjugate to pseudo-automorphisms. In particular, regularizable and find orders and things like this. Right, and I want to advertise two open questions here regarding this. So notably, what we don't cover for this generation question is this case, right? So two unknown cases for this non-generation, right? Okay, so unknown. Unknown, I mean like not generated by these guys. So the main kind of open question here is Cremona 3C. Like whatever, what we don't know is whether it's generated by involutions, for example, or not. Or other types of elements like this. Because we don't provide any abstraction and just unknown. And this is kind of the main thing we'd like to know, because Cremona 4 and higher, it's one thing, Cremona 2 is another thing, and Cremona 3 is not clear. And a slightly less well-known question is Savory-Brouwer surface. So now we're in this column. So S is Savory-Brouwer surface. So twisted form of P2. Yeah, so definitely non-closed field, where you have twists of P2 with no rational points. And the question is, I think it's still open. So the question asked by Jeremy Blanc, Yulia Schneider, and Igor Yasinski is whether this is generated by regularizable maps or not. So what they did prove, based on some earlier work, is that it's not generated by finite order elements. So it's kind of not our line of work here. So our invariants are 0, but they produced a map to Z, homomorphism to Z, which says that you cannot be generated by finite order elements. But the way they do their things is not, they don't automatically vanish on regularizable ones. And that's something which may be accessible one way or the other. So probably the first problem is old and kind of hard, and it's not clear how difficult this is. All the links are classified, so a lot of things are known about this group, but not this thing specifically. So the plan for today is as follows. So there'll be 3 things I want to tell you. First, I'll explain like 2 non-vanishing constructions here. There'll be 2 constructions for non-vanishing for n starting from 4. Then there'll be another application. So this is a standard application, and I'll explain like a new application to special Cremona. I'll recall what this is. Something called special Cremona group over a field, a subgroup of Cremona. And then we'll change gears a little bit, and going back to lecture 1, where I introduced general like additive invariant, I'll explain some more interesting additive invariants, some other additive invariants that we can work with. Yeah, so they will be refining the invariant I was talking about. Most of the applications already happen here, but there are other things we can do and maybe prove other things using them. Not very clear yet. Okay, so let's do some constructions. So the 2 constructions, like one is slightly older one, the other is slightly newer one, and they have different pros and cons, so I'll explain what they are. So first construction is so-called Hassett-Lie map. In Cremona 4, okay, so over C. So basically, for this kind of arguments, one needs to generate interesting links, just interesting maps. Yes, and they have produced a map like this for some other purposes. I'll now state what it is. So you start with P4, and you look at a very specific surface embedded in P4. So it's a projection of a certain K3 surface, so of a general K3 surface of degree 12, a very specific thing. Degree means it used to be h squared equals 12. It used to be living in some higher dimensional projective space that you projected down to P4 in a special way. And I won't go into details, so it won't matter exactly how we project it, but there's such a surface. And then they look at linear system of quartics passing through this surface. And it so happens that this surface is a complete intersection of quadrics passing through it. So there are some easy things to compute here, and the easy thing is how many quartics there are, and you end up mapping into the other P4. There'll be this many members in this linear system. And because it's a complete intersection of those quadrics, the map is resolved by blow up. That's another standard thing. So you blow up this, you get some fourfold on top, and then you get a morphism here. And the non-trivial thing is to analyze this morphism. Even though that's relative pk rank 1, so this is relative pk rank 1, but whether it's a blow up or not, and what is the center, you need to see. And what they've done is it looks symmetric. So there's another surface looking like this on the other side. So also a K3 surface. And the point of this construction is it's just a different one. So S is not birational to S prime. So it's among K3 surfaces, there's certain interesting equivalence relation called derived equivalence, and this is the derived equivalent partner of S, the only one. In lower degrees, there will be no such things, and it's the first degree where an S has a derived equivalent partner. So they are derived equivalent. So not birational, but derived equivalent. So there are some subtleties here which I'm hiding. So these surfaces are mildly singular. So therefore, I'm saying birational, not isomorphic. So birational means smooth models are isomorphic. And also, derived equivalent will apply to the smooth models, not to the surfaces themselves. Say again? So, the divisors will be ruled over these two surfaces. And because the surfaces are different, the divisors are different. So yes, so let's do this computation. So what I want to say is that because that's a blow up, even though it's not a smooth surface, but generically it's smooth, so as a birational type, we end up earning P1 times what we blow up, and then minus what we contract onto. Right? And then what I'm saying as usual is this is not 0. Right? And now we have all the tools actually to see how this goes. So how would this be 0? This would mean that these two threefolds are birational. So assume that they are birational. And then we can run the MRC fibration as I was explaining yesterday. So because K3 is non-uniruled, MRC fibration is this factor. And the MRC fibration being functorial means that you earn a birational map here. But we assume they're not. So these are MRC fibrations contracting this rational dimension 1 thing onto the non-uniruled base. Yeah, so this is the point. So these links are kind of complicated, and one needs to work hard to find them. And for example, for P4, there is this, and one more construction I'll explain, but it's not like so they're hard to find, basically, such constructions where the centers are not matching up. yeah, so basically, Hassett-Lai wrote a whole paper about this construction. I think that's much easier. If you look at some kind of involutions, I think it's much easier to find the same K3 than a different. Yeah, I think so. So as I explained for dimension 3, what we can do, we can just multiply this by P1 and get more examples like this. So take this morphism times identity on some pk, pl, right? Then you get a self-map on p4 times pk into p4 times pk. And the point is that, let's call it big phi. The point is that the invariant for the big phi is still, it's the invariant for the small phi times pk. And by the same argument with MRC fibration, that's non-zero. Just because you have higher dimensional rational direction, you construct. Yeah, so this kind of covers like n starting from 4, at least for complex numbers. Yeah, so Hassett-Lai construct the link over C, and then there's some work to make it over any field. So Hassett-Lai construction can be realized over Q. And Q is the best, so if you want characteristic 0, then it's good. Hence, over any field containing Q, i.e. characteristic 0. Yeah, this is a little bit of work, but once you have descended the construction, and you know that your guys are different over C, they are forced to be different over the field over Q and over the intermediate field. So this is standard thing that, yeah, they cannot become birational on any intermediate field between Q and C. Characteristic P could also work, but it's a little bit harder one. It's whatever. Maybe definitely large characteristic works formally, and small characteristic you need to see what happens with those things. Okay, so this all looks good. So it kind of covers that case, namely any characteristic 0 field and any dimension starting from 4. But there are some disadvantages of this construction, which I want to explain now. So what are the disadvantages of this construction? Kind of what do we want to improve? So there are two obvious disadvantages. Is that the first is constructed elements it feels bounded. So we have like one example is parameterized by a bounded family. So it looks like just one element in the image, but I can vary the K3 surface S, isomorphism class of this K3, and I get some moduli space, so I get infinitely many elements like this, but it feels like it's like the same thing, right? So the question we had for some, not the same thing, but like the question we had for some time whether this image is bounded or not. Because paper like Jeremy Blanc with, like, as I'm saying, these examples are hard to find, and for some time this was the only example. And in this example, the only thing we can vary is the K3 surface S. Therefore, we get a bounded family in the image. And the question is whether, right, right, but like, the target is parameterized by algebraic varieties. Therefore, we can ask whether it's parameterized by a finite type family or not, the image. It's like whether we have freedom only to choose varieties of fixed type to blow up in P4, or we can say that there's no single family, like we can keep increasing the degrees of those surfaces and things like this. I'll explain the example when it's not, like how it works when it's not bounded. So we had this question for quite some time, and now we can give a better construction which has unbounded image. In a way I'll write down in a second. And the other thing is this. So we don't produce, not producing new, genuinely new elements in the image. So if you compare P4, P5, P6, and so on, currently you're getting the same stuff. You're just getting the same K3 surface over and over again. And I'm about to explain a construction which has unbounded image, and for every new Pn, you have something new in the image. And it's interesting for various questions. Yeah, so the second construction then, which will address this, is the new construction, which we are writing down at the moment with Lin, is spread out. So another construction. It will look a little bit more technical than this, because it's kind of should be more complicated. So spread out. And I'll explain what this means if you haven't seen this before. Genus 1 curves, centers for P3 links from P4. So previously we had this situation where if I put a new field here, f, so f is a function field. And we had this other non-vanishing for P3 over function fields. And we're going to make a family out of this in an interesting way. Yeah, so I'll remind you what the construction was, okay, I can tell now that in the P3 case, you end up with curves of genus 1, which are twisted forms but not isomorphic, so they are twisted forms of each other, i.e. if you go to algebraic closure, they are the same. And for genus 1 curves, yes, and they have genus 1. And there's something a bit more specific for genus 1 curves. They are torsors for the same elliptic curve. So there's a elliptic curve here, E hanging around, which is peak 0 of 1 and peak 0 of the other. So in over algebraic closed field, elliptic curve with its own peak 0, but over any field, peak 0 gives you a curve with a point. So this is an elliptic curve. I'm just trying to revise the construction from before. Basically, there are two centers, genus 1 curves, twisted forms, and furthermore, they are torsors, so E was acting on them. So C and C prime are have free transitive E action. Torsors. And the point is that they are not isomorphic over the ground field. Okay, so this is what I want to say about them now. Interesting twists with the same over the same elliptic curve. Yeah, so this will go in the proof of the theorem I'm about to explain. Yeah, this is work in progress, Lynn and myself. We're writing this down. Yeah, so slight disadvantage here, because we're doing something much more complicated than the previous construction. We have restrictions on the field. Right, and then we want to, we will work over any base. Like it will be stronger non-vanishing than just for P4 or Pn. We take any variety over this field of positive dimension. And the point is, in this case, the claim is that the Motivic invariant C is not 0 for P3 times B. So that's the first basic claim I want to make. Okay, I weakened my field a little bit, so it's algebraically closed field, but yet I not just do P4 and higher, I do anything divisible by P3. So it may be easier or harder depending what B is. So definitely includes all the higher dimensional PNs, but also includes some mixed things such as like you can put rationally connected variety, which is irrational, or you'll get more stuff out of this. That's the basic thing, and then I want to address the two weaknesses from before. So furthermore, I'll explain this unboundedness. So the first is image of C, so this guy is unbounded in the following sense. Yeah, so as soon as someone gives you a family of varieties, so family of varieties, and T is also a variety, so finite type family. So T is variety or scheme of finite type, and kind of you're trying to see whether whether your image is hid by these guys or not. And the thing is that it's not contained in the following subgroup. So I'm kind of trying to see whether I'm contained in birational types parameterized by this base. I'm looking at all these guys. So for every closed point, I'm looking at the corresponding fiber. Okay, I'm assuming they're correct dimension, assuming they're divisors for this kind of thing. And the claim is that the image will not be covered by any such bounded family, as opposed to the previous case where it seemed like it was covered by K3 surfaces. And in fact, for some time, we wanted to use some kind of Birkar bound, like BAB conjecture, like in other works in this field, to bound this, but the outcome seems to be the opposite. It's just not bounded. So that's the first improvement. And the second improvement concerns what kind of types we get at the image. So this is saying we get like infinitely many and unboundedly many. And the other thing is that the image grows when the dimension grows. So I want to say that image of C contains, infinitely many, but the point is not infinitely many, but that there are classes of varieties which are not ruled, not highly ruled. So I want to use this rationally connected dimension from yesterday. So if you have an MRC fibration, you're asking for rationally connected dimension, so dimension of the fibers of the MRC fibration. 1 is very small. 1 means that your MRC base is almost maximal. So here specifically it will be something very more explicit. It will be birational to P1 times non-uni-ruled center. Non-uni-ruled. So this will be divisors produced in this construction. They are, of course, ruled. As I was saying earlier, the image is all ruled, but they are ruled in a minimal way over something which itself is not uni-ruled. So, and in Harris's notation, this is the thing, rationally connected dimension 1. Yeah, and somehow we see that this way we produce new elements at each step, because it will be P1 times something like a base of appropriate dimension, not uni-ruled, not like in this more trivial procedure. I'll explain an application of the second part, which is kind of fun to think about. What's an application? It's a certain thing about Cremona groups getting larger as n increases, and there are various ways of saying this, so here is one way to say this. The corollary of this second part is that for every b over k, and m starting from 0, we can look at beer of PM times B versus the next one. So I'm stabilizing birational automorphism with respect to this factor. So there's a natural map like this by acting trivially on one of the components. Yeah, so I'm doing the same stabilization here. I'm treating this as P1 times PM, and I have this map which acts trivially on the P1 factor. Yeah, and it's kind of more or less clear that they're getting bigger, and then you can sort of measure this in various ways. So the way I want to measure this is that I look at the Bellinizations, and I'm saying is that these maps are never surjective, not surjective. It would be kind of surprising if they were surjective, but also interesting to be able to prove things like this. Yeah, when B is a point, it's an easier statement. So when B is a point, when we just look at stabilization for projective space themselves, so literally Cremona, this was checked by, proved by Markus Schimmick, based on, so main contribution was BLZ, so Jeremy, Stefan, and Susanna Zimmermann. Yeah, so they produce kind of some interesting maps, and the maps they produce there's more at every projective space, but this case is a bit different. So you have arbitrary base, so maybe their proof works, maybe it doesn't, but this is one thing we can provide. So the whole thing starts at P3, kind of, right? So M. Oh, yes. Yeah. Thanks. Sorry. Yeah, thank you. Yeah, very good. My notation got shifted a little bit. Yes. So indeed, so I start with P3 times B, and the next thing is P3 times P1 times B. Right. Okay. Thank you. For small m, it works a bit differently. Yes. So yeah, maybe I need to, so the fact it's not surjective follows from this fact that at every new dimension, we just get different values in the invariant, which are not induced by the previous dimension. So this Z is not divisible by P1, therefore it's not coming from the lower level rational map. So what I'm saying is that when we look at, so the proof of this corollary will look like, we look at invariants here and here, and the image here is provably not coming like this. The image here won't be divisible by P1 enough to come from this level. Therefore, this won't be surjective. So this was surjective, then the image here would be equal to the image of here times P1, but it's not. Okay, so it's exercise to see how this follows. The point is that that center we blow up at the next stage is not divisible by P1. Mm-hmm. 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 Yeah, thanks. So the first thing I want to say is that, I wasn't explicit about this before, but because the image is an abelian group, whatever I do factors through abelianization. So I do control abelianization, actually, through this map. So maybe without abelianization, it's easier statement. Abelianization makes it more interesting because who knows what happens after we quotient by, okay, that's a new ingredient, and kind of abelianization is more interesting because who knows, maybe abelianization becomes 0 at some point, right? Okay, but it doesn't, but it gets bigger at every point. Yeah, thanks. Yeah, so the invariants we work with are vanishing for regularizable maps and also for the commutators. Therefore, what we do control the best is abelianization modulo everything regularizable. So we make claim about things like this. Okay, so this proof is a little bit technical. I'll give the main steps. So the point is that, yeah, so we do that thing, and we need to control. Yeah, okay, so I'll say some words about this spread out construction, which is a useful technique to know. Control these curves over the field, which is now a function field of the base, right? So now naturally have the small field, like the field K I work with, algebraically closed, and this field F. Right, and then the spread outs is their B models. And their B models, which I denote as J, Y, and Y prime. What I'm saying is that in some sense, to give a variety over this function field is like giving a morphism from a variety to a base B. Like specifically, if you do have varieties over the B, you can pass to the function field. So what I'm saying is, I want this guy. J is like some kind of the elliptic curve one. And the other guys are the torsors. So the first thing I'm saying here is that if I have some kind of families over B, I can take the generic fibers, and I want to hit my curves. So this is like dimension 1 fibrations, and from here I can go to these curves. And conversely, if you have such curves, you can take in a fine model, maybe resolve everything and get morphisms like this. Yeah, so to give a variety over this function field is, you can then make a choice of an actual variety over K with a morphism realizing this generic fiber. Okay, this is called, okay, this is a version of spread out. There are more complicated versions of spread out also. Right, so yeah, why do I call them like this? So this guy has a section. Yeah, now all three of them are elliptic fibrations. So my generic fibers are genus 1 curves. So what I expect from these morphisms, they are elliptic fibrations, but the difference is one of them has a section and the other two don't have a section. So kind of maybe after base change, they will be the same, but over this base, they're just different. Yeah, so basically, the proof proceeds in constructing interesting elliptic fibrations with a section over B, and then twisting them, and then doing, applying that construction. So, like, the step in the proof is to construct infinitely many or unboundedly many types of those J's. So specifically, one formulates as follows. For any T starting from 1, so here is the unboundedness coming. I want to construct such an elliptic vibration with a section so here, by elliptic vibration, we can be creative. What this means, definitely generic fiber is a genus 1 curve. We can ask it for it to be flat or non-flat. The point is that everything is birational with respect to B, so it doesn't matter very much. But the thing you can imagine is that all fibers are elliptic curves, for example. And it will have a section, so it will correspond to that elliptic curve, and these two guys are the twists. Such that, okay, and there's some properties. Like, one needs to set up enough properties to make this a convenient variety to work with. And the first thing to say is that this is an Ithaka fibration. for this space. So Ithaka fibration is what you get from the canonical linear system. So you look at all like a pluricanonical map, so map given by powers of k. If you are maybe rationally connected, you don't get very much. If you are general type, you get a lot. And then here, I want to get this elliptic fibration. So what this implies in particular is that this is canonical, so intrinsic for my variety. Because in principle, the same variety could have a lot of elliptic fibrations, and it's kind of a problem in this thing, in this business of spreading out. You want the fibration to be unique. And this is one thing it implies, that this variety knows its fibration. And the second thing it implies is that the Kodaira dimension of this variety is the dimension of this base. That's, in fact, definition of Kodaira fibration, that you look at pluricanonical linear system, see where it goes, and this is the answer. So kind of it's a thing which is not, so what I'm saying is it's positive, hence JD not uni-ruled. Yeah, so kind of it's far from rationally connected. And second is, so yeah, this helps us working with this elliptic fibrations. The second part is that these guys are unbounded. So I have this D and J invariants of psi D are unbounded. So what's a J invariant of a fibration? J invariant of a curve is an element from the field, but now our curve hangs over the generic point of this, and J invariant is whatever kind of polynomial you get there, and the point is that we want them to be unbounded. Yeah. So kind of the point is that we cannot parameterize all those guys by a single family. The degrees of the J invariant maps are unbounded, yes. Yeah, there are some subtleties how to define it properly, but the intuitive meaning is that J invariant is some kind of polynomial in your variables here, and it should have unbounded degrees indeed. So maybe even at this point, even if it was characteristic P, we could choose a nice fibration here. So maybe a quasi-elliptic wouldn't appear just because we don't pick them here. We are free to choose the one we want. But there are some various subtleties and various points, such as, yeah, so typically, such as even when our field is perfect, the field of functions over it is not perfect. Okay, anyway, but okay, for some people it's not a problem, but with this elliptic, working with these elliptic fibrations is harder over non-perfect fields, yeah. But yeah, so I think in some sense you're right, yeah. Okay, so we construct this, right, and there are some other properties which don't specify because I won't use them explicitly because I don't give enough details in the proof, but the point is that you take, so okay, this D, its only role is to make unboundedly many of something, so we work with one D at a time, and unboundedness is taken care of here. So we take J to be JD for some D. So I don't keep using this J. And then, right, so what I said earlier is I look at the generic fiber of my elliptic fibration. That's an honest elliptic curve. So it had a section before, now it has a point. So with a point. And then we can construct twists C and C prime. So we kind of go sort of there. So I want, so my function field is this. I want twist to have no rational points. And this is kind of arbitrary twist. And the other twist is, okay, pick 2 of C, another twist. So I'm not sure if it will help people or not, but the way I think about this twist is as follows. So if you have, okay, a little number theory interlude, arithmetic interlude, so you look at the elliptic curve. Actual group, yep. So this is like, these twists are living over this function field, and in a second I'll spread them out. So far, so I'm going back and forth between. So a little interlude on the Shafarevich group, Tate-Shafarevich group. Elliptic curve is a group scheme. And there is something called Shafarevich-Tate group, written as Russian Sha. So Shafarevich-Tate, or Tate-Shafarevich, which parameterizes, so it's a group, and it parameterizes E-torsors. So the set of E-torsors has natural group structure. It's a certain Galois homology group. And why am I saying all this? I'm saying this that these two curves are related in a certain simple way here. So if alpha was the class of C, then 2 alpha is the class of pick 2 of C. And my class I was choosing was non-zero. And furthermore, if you remember, I wanted degree 5. I had elliptic quintics. So I had order 5 class. And so you look like, order 5 class, and you double it, you get a different class. That's kind of what happens here. If it was order 2, you would kill it. If it was order 3, it would be actually the same up to sign, but that's the interesting case. Okay, I'm not sure if it helps or not, but this is how this works. These torsors live in a certain group, and taking this relative picars takes a multiple. And if you take multiple coprime to the degree of your minimal degree of rational point here, you have a kind of a natural partner of that guy. Okay, so interlude on number theory over. You can ask me later if you're interested. Then we spread them out to those guys. So then take models y and y prime as above, as in the diagram. So like curve over this spreads out into some elliptic fibration. Yeah, and then we're ready to go. So we just say that now we have P3 times B, and I want to go into P3 times B over B. So I'm about to produce some maps from P3 times B to itself, from the maps from P3 to P3, and nicely over B, so that I have no problems with twisting this base. Okay, so before I said we're blowing up this curve. Now we're blowing up this elliptically fibered thing, and 2 different ones on the different sides. So all that construction with the curve is now spread out over this base B. And instead of blowing up a curve over in P3, I'm blowing up this thing over B. So it's some kind of horizontal blow up. And I call this big phi. And at this point, it's convenient to use this vertical and horizontal terminology from last time. Specifically, we can remember that C of this big phi is equal to the horizontal part and the vertical part. I have a fibration, so I can talk about this. Okay, and so one of them is vanishing. So there were 3 vanishing results yesterday. This was called vanishing 2, right? Because I have map over the base, and I'm looking at vertical invariants, and they always cancel. So this was called vanishing 2 yesterday. And we'll use it once again later today, so you can remember that over the base means vertical parts vanish. Okay, so this is very good, because horizontal one is the one we know, actually. So it's convenient to separate them like this, because we'd like to say that everything happens over the generic point of this base, and now we're allowed to say this. So the horizontal one, by definition, is we have to take the generic point here and look at what we've done before. So what we end up with is C of this little phi. And little phi was that, so restriction to the generic point. it looks very good, but it's not quite done yet, so we have to think what we achieve. So we blow up some model of y and contract onto some model of y prime. So there's no problem in writing this. Right, so this is how the horizontal invariant is defined. We just do this. We take whatever that thing was, and then do restriction of scalars, and the restriction of scalars is taking this model. Restriction of scalars from the function field to k is this class of this and class of this. Yeah, and we have to say y is non-zero. I mean, and there's a little bit of kind of work going here, so I need to explain why this is non-zero. Okay, and here everything comes together, so two things. So first of all, let's say they were so 0 means they're birational as usual. So assume they're birational. So by this assumption on Itaka fibration, okay, this was for the one with the section, but it's a numerical thing, so actually these two guys are also non-uni-ruled. Right, so I constructed the main, this main guy, which has positive codaric dimension, but the same will apply to these two guys. So MRC fibration will imply that they are themselves birational, this basis. This is looking even better. Now we have to think, what about how we pass to the generic points? And in principle, if this elliptic fibration wasn't canonical, we would be stuck here. But in this case, because these are Itaka fibrations, in particular, we get a map like this. So yeah, like with a little bit of work, one can get identity here. I want to say that I want to pass to generic points. So I had this just birationality, and I want to say it will respect these Itaka fibrations and will give me birationality of the curves, but then we are done because this is not true. This is false by assumption. Yeah, so we know the generic fibers, and in these two steps, we also control this spread zone. Okay. Yeah, so, okay, we'll look at the statement of the theorem once again. As I said earlier, this unboundedness comes here in the degree of the J invariants. And the second condition is because we visibly get something of the form P1 times not uni-ruled, therefore it satisfies that thing with Y for Z. A little bit technical, but this is the idea of the construction. Yeah. For this. So here I'm passing to the generic fibers, and I'm saying that if my birational map preserves the fibrations, the generic fibers are also birational, just formally. So just it's a formal step, provided that it commutes with the fibration. So this was the most technical part of today. We'll do some easier things now. Yeah. Yes. Yes, that's fine. So scheme of finite type. This is what we're proving. Actually, I forgot that my varieties are scheme of finite type. This is standard. That's the standard way to say a family. Like what Birkar proves a lot is like whether something is parameterized by this or not parameterized. Okay, so we'll do some kind of easier to appreciate things now. So we'll do applications to special Cremona. So I have to remind you what special Cremona is. So that's a certain subgroup inside Cremona consisting of maps which preserve the volume form. So volume form is the standard torus volume form, top form on the torus. Yeah, so that's interesting subgroup inside Cremona, consisting of this kind of elements. So what kind of stuff do we have there? So we have there definitely scalars. If you multiply coordinates by non-zero scalars, this volume form doesn't change. Yeah, so we get a torus inside there. Then we get S, L, and Z. And these are monomial birational maps, which already appeared in some other talks. Monomial maps. And I look at determinant 1. And it's kind of interesting that this works. So let's do an example together. Example is, yeah, just to give you a flavor for this, how this group works. So I look at matrix 2, 1, 1, 2. I make it symmetric so that I don't get confused with the transposition. So what I'm saying is xy goes to x squared y, xy, right? And it's a little exercise for us, so let's see if this works. So we're supposed to do d x squared y over x squared y, wedge dxy over xy. Yeah, so I chose a matrix to determinant 1. And so I get 2xy dx plus x squared dy, wedge y dx plus x dy. Yeah, and basically now I have to collect the terms, so I'm getting this, and then minus, because they anti-commute, x squared y. So it will be 2x squared y minus x squared y divided by x squared y, and then all divided by xy, so it works. So if you had determinant minus 1 instead, so if you look at GL to Z, such as maybe transposing them, you get a minus sign. Right? So this is why you look at SLN. So this was example for SL to Z transformation. So I'll tell you another source of special Cremona maps in a second, but these are the standard kind of two things. And altogether, right, so maybe I should use this notation. So these generate some subgroup inside automorphisms of a torus. So special automorphisms of the torus. So inside automorphisms of the torus, regular ones, we have both scalars and also actually GL and Z. And let us call special automorphism of the torus subgroup generated by these two factors. Okay? So special like in the special Cremona, so preserving the volume form. So what is known about this group? Like in dimension 2, there's an interesting theorem. When K is C, there's a, okay, so it was a conjecture of Usnich who was coming from a different field. He was doing mutations of Laurent polynomial and then proved by Jeremy. That the group is generated by, it's a bit like Castelnuovo-Noether, generated by special automorphisms of the torus. So namely, maps like this and maps like this, and one more element. And this element is is this. And it's a pleasant exercise that its order is 5, it's a finite order element, and it's regularized on the best of degree 5. I don't know, maybe it's also exercise. Definitely harder than this. Okay, right, so, and in general, one wants to know, okay, like just for the Cremona, what are these generated by? And I think this is the only generation result we have at the moment. So let me give you another source of examples of these special Cremona maps. These are called standard mutations. Phi A inside special Cremona and K. So for that, you fix a rational function A in n-1 variables. It's a bit like de Jonquière. So you'll act on just one of the variables. So phi I of x1 up to xn minus 1 xn, it fixes the first guys, and the last one multiplies by A, right? So these are called standard mutations. So, and then it's this is easy to see that, of course, the volume form is preserved because we'll be taking d of this, and it's only relevant in this variable, and we divide by A. So it's good, because we have to divide, we have to multiply by A and divide by A. So this blank Motivic map is, so note, tau can be replaced by standard mutation. So you can, if you make some coordinates changes from special automorphisms, you can trade that map for a standard mutation like this. So in this case, the special Cremona is generated by automorphisms and standard mutations. So why did I start even thinking about this? So last month, Corti in the CIRM conference asked the following question. Corti in CIRM in 2025, where some of you have been present, he asked, yeah, kind of, I think, motivated by the invariants. He asked whether special Cremona is generated by special automorphisms of the torus and standard mutations. So, like in dimension 2. Yeah, and kind of we're in the position to deal with this question. So the main step was done before, specifically, so after we introduced invariants, like recently, there was this application to Byloginov and Zhang, which who proved that C restricted to special Cremona. So I was telling you about non-vanishing on the big Cremona, and on the special Cremona, one needs to check, right? And they proved that it's not zero under similar assumptions to what I was explaining. So either n starting from 3 and k is a small field, so namely number field, so exactly the field like in our theorems for the same reasons. Or n starting from 4, and they didn't do every field, just complex numbers. So what they've done is they took our maps, like elliptic curves or Hassett-like A3 surfaces, and they conjugated them on the left and on the right to get special Cremona. There's kind of a lot of work to put our maps in this group. They naturally don't belong there. And one has to pre-compose and post-compose, and magically one ends up with a map here with the same Motivic invariant. And this is why it is these fields, because they check, they do the same maps, but it's a lot of work to put them in here. It's a recent paper from last year, 2024. Okay, so as you may expect, I did use a corollary that were not generated by Cortis standard mutations. So corollary, Cortis is a negative answer. So that's kind of a standard business in this field. Someone asks a question, and then you need to answer it negatively. So it's good when people ask questions, even especially when the answer is negative. So, right. So, yeah. And there's this interaction that Corti is interested in this from different reasons for mutations of Laurent polynomials in mirror symmetry, and there's this interplay back and forth between what the questions are and what kind of invariants there are. Anyway, in the same assumptions as Logan or Zhang. And in that theorem by Logan. Okay, so we have all the tools. So we have to, yeah, I just explain why the invariants vanish on those maps, right? So obviously, because we have automorphisms here, then the invariants are 0. No matter what n is, it's automorphisms, nothing. Right, and then I have to look at standard mutations. And the standard mutations are these beautiful maps which preserve a projection, right? So we have GMN. So look, I can look at Pn, or naturally we can look at the torus here. Birational map from a torus to itself, preserving almost all the coordinates. Literally preserving them, not twisting them, right? So I have the projection onto the first n-1 coordinates, and I commute with that projection. Yeah, so maybe we can argue directly that the invariant is 0, but it's convenient to use this vertical and horizontal vanishing as I was introducing. So we have horizontal and vertical. Yeah, so this is the last time we use vanishing 1, vanishing 2, but they are literally those two. So this is what I was calling vanishing 1, because my fibers are curves, therefore nothing happens in the horizontal direction. And it's convenient, like, so this was a flexible statement. I didn't have to assume these are proper maps, for example. I don't have to like completify and then do things. So I can just apply it here. So fibers are curves, therefore no horizontal contribution. And this was because we go from fibration to the same fibration, preserving the base. This was 0 by what I called vanishing 2. Yeah. So maybe one can prove it directly, but it's a nice kind of way to think about these maps. Yeah, but as I'm saying, the main contribution is that theorem. This is more like nice corollary. And I think people should look more at the special Cremona, so not much is known. It's not such a widely studied group as the usual Cremona. There are probably lots of questions we can ask and answer about it. Okay, that's what I want to tell you about special Cremona. The last part for today is some other invariants. So I'll speak about, hopefully, 2 other additive invariants. And we're kind of going back in time. So lecture 1, if you remember, we had this universal invariant. So if you recall, I was talking about additive invariants to various abelian groups. And these were like n-dimensional varieties. And yeah, I was told that I need to put different n here every time. So not the same value, it depends on n. And right, so the kind of universal one was this K0 of pairs, which wasn't showing up recently, so let me remember what it is. So K0 of n-dimensional pairs, it's generators and relations as usual. Generators are open embeddings, and relations are compositions. So if you look at V into U into X, we go V into U plus U into X. Right. Yeah, and like what I proved in the first lecture was that there is such an invariant which literally sends an open embedding. Yeah, and there were some complaints regarding like source and target. So what I mean is defined for all x and y, and I fix it on the open embedding, and this is sent to the class of that open embedding in this group. Yeah, and in some sense, one can show it's a universal additive invariant. So, and I said we'll then project down to birational types, namely this Burn n-1 of k. And most applications can live here already. But in fact, we can project to some other things and get other invariants which one can still explore. So the first projection was just taken open embedding, and the second projection was taken the complement. Sorry, say it again. What's your question? That's right. So, like, yes, indeed. So if I have, I want to fix this on an open embedding, and then what you're saying, indeed, is that if I have an arbitrary map, I can factor it into two open embeddings, and then take the difference of this minus this, right? But kind of what I was saying is it suffices to fix it on this generating class, and explicitly this will be this minus this. That's right. Yeah, this was kind of the main particular case. Here the projection was taking the difference, divisorial components of the difference. Okay, so I want to compare it to to Genevois, Lonjou, Urech invariant. Christian, did I spell Genevois correctly? Right, so yeah, basically I want to explain the specialization of this, which will be their invariant. Let me remind you what their invariant is. So what they do, and what Christian may explain tomorrow, is using cut-zero complex, they construct a certain homomorphism to a free abelian group, which is like a bit better than this, or substantially better than this. Instead of just remembering birational types of divisors, you remember how they sit in X. You look at divisors in X modulo birationality. So let me explain what this means. So these are prime divisors in X. And this is a relation that we say that two divisors in X are equivalent if you can find a self-map which sends one of them onto the other one without contracting it. So there are exceptional divisors and non-exceptional divisors, and here it's supposed to be non-exceptional and one mapping into the other. So there's a birational isomorphism between divisor and induced by, I guess they call it Cremona equivalence, but this is this kind of birationality of pairs. Yeah, and the definition is that it's the same thing, kind of as here one takes arbitrary map from, yeah, okay, one can take arbitrary map from X to X for these purposes, and then you look at divisors contracted, divisors created, and you look at the, you send phi onto the difference as usual, but in a better group, in a better kind of target group. So di minus dj. Right, so you look at the ones on this side with the plus, the ones on this side with the minus. Yes, instead of birational types, you remember how they sit in X. So what I'm saying is that there's a forgetful map here to the Burnside group. And then this composition is our invariant. So they provide a lift like this. Yeah, and then one wonders whether one can prove more non-vanishing using this refined invariant. So far, it's a bit hard. So far, examples usually happen here, and we don't know what's the difference between this. But it looks a lot stronger. Yeah, so I want to explain that is that this actually also an additive invariant which also factors from these pairs. Okay. We'll see. So, right, so kind of this construction inspired us to think about more universal ones, and then we are getting this and the projection. So let's see. So I want to do the following. So I want to look at, from K0 of pairs, I need to construct some realization into group which should look a bit like this, but the difference is I have to allow moving source and target, not the same X. So, okay, it will be free abelian group on something similar, but I have to allow changing X. So, I'll write divisorial pairs, modulo birationality. Let me explain what this means. So divisorial pair, again, is a divisor in X, so prime divisor, but X is not fixed anymore. And, okay, so this is dimension n, this is dimension n, so this is dimension n minus 1. Right, and the equivalence is that kind of same relation, so Cremona. I want to say that xd is birational to x prime d prime if there's a map from x to x prime sending d to d prime without contracting it. So it's the same thing, but now the target is yeah, so let me call this map T, and what it does, it does the usual thing. It takes divisorial components of the complement, so D1 up to Dm are divisorial components of the complement. So this is how kind of this map C was defined. We're looking at divisorial components, and now we do the same thing, but in a slightly better group here, up to this relation. Yeah, and then you need to check that if you have an embedding V into U into X, your divisorial components add up in this target, and they nicely do add up. So there is such a well-defined homomorphism. So what I'll need to be checking is what happens when I have V into U into X, and one checks this. Yeah, I wish my co-author Lin was here and explain this, because it really was his contribution, his insight to notice this. He would explain this better. Right, so anyway, the exercise here, once you have set it all up, is that if you look at T composed with A, right, so if you do this, after you do this, and then you look at self-maps, then you get GLU invariant. So just formally, if you restrict to self-maps, by definition, you get that, and that's application. But as I was saying, it's quite interesting to try to explore the difference between the two. In particular, one wants to know whether one can use this for P3 over C. This is maybe a natural guess, something which is open, but I'm afraid it won't work, so I have a joint collaboration, ongoing collaboration with Julia Schneider and Socrates Tsikas, where we prove that for threefolds, these two invariants are really the same. So unfortunately, it looks like for threefolds, there's no new contribution over closed fields. Okay, so I explain one last application and one last invariant. And this is actually the field where I'm coming from, so that's final application. Is the Grothendieck ring of varieties. So it was the ancient concept due to Grothendieck in the 60s, and this is the first, like the first version of motifs Grothendieck came up with, and then he just abandoned it. But, okay, that's some kind of interesting ring where all varieties sit, and since then a lot more complicated motivic theories have been developed, but for some people that's still a motivic ring. Right, so I have to remind you what this is, and straight away I introduce some kind of truncated version. So this is motivic techniques, and we like doing this sort. Okay, one of the very basic things what you do is universal constructions with quotients. Okay, and that's kind of one of the first such things in algebraic geometry, I suppose. So you look at isomorphism classes of varieties of dimension up to n. You can kind of look at some kind of infinity, but all varieties, but it's convenient. It's important for me to bound the dimension and compare them at different levels. Modular cut and paste relations. And cut and paste relation is very similar to things we've been considering in this lecture. So you look at an open subset, and then you and Z is the closed complement, and then you declare that X is equal to U plus Z. Yeah, it's a little bit subtle. It doesn't make much difference what you mean by varieties. So the most natural thing, you just put schemes of finite type here. And then like, you can do arbitrary like certifications and have classes of schemes of finite type in this ring. And you always get the same thing no matter whether you put quasi-projective or varieties or schemes of finite type, because it will be insensitive to non-reduced structure anyway. Okay, that's some kind of thing. It sort of tells you about like all varieties, how they glued from pieces, so lots of content. Right, so then you define K0 varieties without any bound here similarly. So just without putting any bound on n. And then it's a ring. So it's a ring under product. If you truncate them, you cannot multiply arbitrarily, obviously, but there's some kind of partial multiplication here. Okay, so I want to give you some properties, some like applications of the invariants to these structures. So maybe before that, let me give an example. Like, it's a ring where it's fun to do computations. So let's think about some classes here in this ring. So the first thing, okay, there's this Lefschetz class, A1, Lefschetz class. And then it controls some properties in this ring. So okay, you can look at P3, for example, and that's a geometric series in L. There's A3, A2, A1, and the point. 1 is a class of a point. Okay, so now let's look at two examples I mentioned in the past here. So intersection of two quadrics in P5, that's a rational Fano threefold. And I gave you this blow-up, blow-down construction, and it's a fun exercise to see that its class is 1 plus L times a curve plus L cubed, where C is genus 2 curve associated to X. Yeah, blow-up, blow-down gives you this. So instead of this term, you get middle Hodge structure. And non-trivial example is, if you look at cubic threefold, which is not rational, as I mentioned, then we don't know what kind of shape it has. So we don't know whether it's like 1 mod L. So 1 mod L means it looks like this 1 plus L times something. And we don't know this because that's equivalent to stable rationality question for this X, whether X times Pn is rational or not. Yeah, so cubic threefolds are not rational. Their stable rationality is one of the big open questions here, and in particular, by some theorem about Grothendieck ring, it's equivalent to cubic threefold having this shape or not. Yeah, these two were easy computations, and some theorems go in here. Yeah. So if you have maybe let's make it more precise, you have a variety, irreducible or not? Yes, it's an irreducible variety whose class equal to 1. You can get it at dimension 1, and then dimension 0, and then dimension 0 will mean it's a point. Yes. If your irreducible variety has a class 1, in general, there's some kind of dimension you can compute, but if you have two classes, X and Y, it's a bit hard to know whether varieties are the same or not. That's complicated. Okay, so I want to define an additive invariant and then state a theorem relating it to these groups. So I'm starting with this universal thing, K0 of pairs, dimension n. And I want to descend to varieties up to dimension n minus 1, where X and Y are n-dimensional. And so basically, here you look at an open embedding, and now you keep the whole class. So previously I was saying, look at divisorial components. Now let's just look at the complement. The class lands here, look at the class. So the relation with the previous thing we did with the Burnside was that there's a natural projection here which picks up the top birational class. It just ignores all the smaller dimensional contributions. There's a natural projection, and previously this was our C, right? So we go like this. And this is what we call C tilde in the paper. Yeah, so kind of lifting of C into here. So it's easy to see that if you have a complement, if you have a composition of this, then complements add up in this group by definition of this group. So it's like everything is like built into work. So it's obviously a homomorphism from here to here, and then the composition is obviously our previous map C. So that's another refinement, like this GLU invariant was one refinement of C, and now that's another refinement which we can consider. So yeah, so I want to relate this to that situation. Specifically, I want to look at the map from varieties up to level n-1 and to varieties up to level n. So for every n, I have such a iota group homomorphism, which just considers varieties of this dimension, up to this dimension, as varieties of one dimension higher. And this all maps into final K0 varieties. And K0 varieties is like, I wouldn't say the union, it's more like a direct limit of these guys. And I'm not saying the union because these maps are not injective in general. And kind of now I'll explain in which sense they're not injective. So what happened, yeah, like how they can be failed to be injective in principle. It means that you look at some n-1 dimensional varieties, but then you start throwing in higher dimensional cells on top of them. And you get new relations here. It's hard to come up with easy examples, but indeed they're not injective, and now we're saying precisely what's the kernel. Yeah, so I'm describing this kernel of this map. So it's the sum of, yeah, I'm looking at all values of this enhanced invariant for all varieties. So n-dimensional varieties, then we're landing in this n-1 dimensional group. And what's easy to see is that this thing isn't the kernel. If you start looking at this image in the higher dimensional one, everything will cancel. And what's interesting is that you get exactly the kernel, right? So I'm not proving this, some kind of a formal statement, which one checks with a little bit of work. But the corollary of this, because we know non-vanishing of the C tilde from non-vanishing of C, we can deduce various interesting things. Specifically, okay, maybe I'll very briefly say that the first two of this, iota 0, iota 1, are injective. And maybe here you need to use perfect field for the same reason as before, because kind of what I'm trying to do here, I'm trying to cancel curves into surfaces. This Gromov cancellation question, and the positive answer there is for perfect field, and vanishing of our invariant here says, okay, C is vanishing, but C tilde also can be shown to vanish with a little bit of work. And then the higher ones are typically not injective in general. This is just because we have non-vanishing for C, then non-vanishing for C tilde under exactly these dimensions. And that's a good place to stop. Thank you.
Yeah.
So for the special Cremona group, you made a choice for the volume form. You took dx over x, dy over y. There are many other volume forms. I mean, for instance, in P2, you can take a volume form with simple poles along a cubic curve.
So for every volume form, there's a special Cremona group.
Yes.
And
I mean, the special linear group is well defined, but the special Cremona group is not well defined. It depends on the choice of a form. So can you say something for the other forms?
I don't know anything about it. I don't know if other ones have been studied. So there's this volume preserving business by Corti, Carolina, Roach. Yeah, so people study two things in parallel. One is volume preserving, the other is some kind of Calabi-Yau pairs. Yeah, so I suppose there is a more general concept of a birational map between Calabi-Yau pairs, where instead of fixing this volume form, you fix a divisor, boundary divisor. And right, so then there's Sarkisov program for this pairs by Corti and Kalogiros. And this has to do with Ugizo's question about quartic moving into another quartic. And I think in principle, one can apply these technologies, but I don't know what are the interesting questions about this group in this context.
Yes.
they relate tori to volume form? So we have one where we have both a torus and the volume form, but in general, for every torus. Okay, okay, okay.
And I think the same for the nation tree by Lucas too, because he proved that every Calabi pair to 3D of regularity zeros was rational, so it's the same thing. You have just one of this.
Mm-hmm.